Now we need to look at a few more problems, and there is a twist to these problems in terms of what we have been doing. So far as we have learned how to use the first derivative to find our critical points, and then we can go in and analyze the first derivative and determine whether their critical points are a relative maximum, a relative minimum, or possibly a neither. And of course, the procedure is you take the first derivative and then you set the first derivative equal to 0 and you solve that equation. And those solutions are the critical points that we analyze. And the key thing, let me write it here. The key thing about critical points is oftentimes at critical points, for instance, if you have a maximum here, on the left-hand side of this maximum, the slope is positive, it's increasing, and on the right-hand side, it's negative. And that's why as soon as we determine a critical point, we looked at the first derivative on either side of the critical point, and then we can figure out what's going on. In the same way, if we have a minimum, we go look to the left of our critical point, and in this case, we would see that the first derivative is a negative since the slope is negative and it's decreasing. The right side is a positive, and then we're able to determine that we have a minimum. So you can see at critical points, what we're trying to determine, we're trying to see if the sign of the first derivative changes. If the first derivative goes from a positive to a negative, we know we have a maximum. If it goes from a negative to positive, we know we have a minimum. And sometimes we have a critical point, and on the left side, in this case, first derivative is positive. We go check the right side and it's also positive. So that's where we have a neither. This is a critical point. The first derivative is 0 at this point. This function is level, or it's flat, it's horizontal. So critical points, we determine these critical points, and then we go analyze what's going on either side of the critical point with our first derivative. Now, rational expressions add one extra complication. So in a few minutes, I'm going to work through 3 different problems. Now, if you recall a rational expression, basically I like to think of it as it's like a fraction where you have some variables in the bottom. Oftentimes the variables are in the top and bottom. So here's the 3 functions we're going to analyze. Here's the first one. The second one is x squared over x minus 2. And then the last function we'll look at is x squared over x squared plus x minus 6. So these are all rational functions. So there's an extra step when we look at the first derivative with these kinds of rational functions. We actually do go find their critical points. So we are going to take the first derivative of the function and set it equal to 0 and solve for it, and we will find critical points. But there's an extra step. There's an extra factor we have to take into account. Normally, when you have rational expressions, you normally have your function, if you graph it, you may have like what I call a break or a gap. That ends up being called like a vertical asymptote. So most of the time when you have rational expression, I'm just sort of making this up. You may have your function looks like this, where there's a break or a gap, this vertical asymptote. What we have to do is now we're going to go find the critical points, because the critical points are where the sign of the first derivative can change. But when we're looking at a rational expression, we also have to take into account any vertical asymptotes. Vertical asymptotes are the values of x which would cause the denominator to be 0. So when we do these problems, we are going to take the first derivative and we're going to find the critical points, but we're also going to go find the vertical asymptotes. And then those are the points that we have to see what's going on. I think it's easiest just to do these 3 examples and you'll see what I'm talking about. Let's do this first one. So let's say we're given this function and we're asked the typical kinds of questions. We're asked to find where is the function increasing and decreasing? Where are there any relative maximums and minimums? That's typically the kind of thing we're asked. Whenever you have a rational function, the first thing I'm going to do is, in looking at the function, I'm going to go determine if there are any vertical asymptotes. So once again, a vertical asymptote is the values of x that cause the denominator to equal 0. Because in a sense, what we're really doing, we're really saying we cannot allow x to be this number. We can never divide by 0. So we call those vertical asymptotes. And when we find a vertical asymptote, we draw this vertical dashed line, which basically says, hey, the graph cannot touch or cross a vertical asymptote. So the steps to solve this kind of problem is, I'm going to put the first step as find if you have any vertical asymptotes. So for this one, it's pretty straightforward, right? If I'm looking at this denominator, what value of x would cause this denominator to be 0? Well, since it's x squared, obviously, I have a vertical asymptote of x equals 0. And then we go ahead and find their critical points. And of course, we do that by taking the first derivative, setting it equal to 0 and solving it. So let's go and do that for this problem. Let's rewrite. We could use the quotient rule, but how about I write it like this, and maybe I can use the power rule. So the first derivative is bring the -2 down front and you subtract 1. Looks like a -4 over x cubed. So to find their critical points, now in just looking at this, hopefully it's obvious to you that there actually is no solution to this equation. One of the things we're going to, I will tell you, what we're going to see is anytime if you have a fraction that equals 0 and you're trying to solve it, let me do an example. If I have x plus 2 over x equals 0, a little shortcut is, for the solution, really all you have to do is you take the numerator and you actually set it equal to 0. It's almost like you can ignore the denominator. So in this case, solution is -2. So if I apply the shortcut here, interesting thing is you can take the numerator and you set it equal to 0 and you solve it, but there's no variables in the numerator. And that's why with this little equation here, there's no solution, which means there's actually no critical points. However, we still can do our analysis. Normally, we go mark the critical points, but now we have something new. We have vertical asymptotes. So just like we break up our graph into regions, we had critical points, we can also break up our graph into regions with vertical asymptotes. Now, in the remaining problems we're going to work, you'll notice, I believe with these last two, we will end up having both some critical points and some vertical asymptotes. We have both. Turns out this first problem, we don't have any critical points, but we do have a vertical asymptote. So I still have to go to my chart and I'm going to mark where I have a vertical asymptote. As a matter of fact, I normally, this is just me, if it's a vertical asymptote, I put a square around it. So just, that's a reminder that it's a vertical asymptote. So just like critical points, vertical asymptotes will break up my graph into regions. So in this case, I have two regions, and now I have to do the same thing I always do. I have to choose a test point in region 1, I'll choose -1, and in region 2, I'll choose 1. And now I'm going to go and analyze the first derivative in each of my regions. So in region 1, here is my, I'll write it up here, here's my first derivative. If I plug in my test point of -1, -1 cubed is -1, and negative by negative, this ends up being positive. Region 1's a positive region. Sorry about that. My phone went off. So anyway, region 1, I've determined it's a positive first derivative. It's like function's increasing, it's going up. Region 2, I choose a test point of 1. So I plug in 1 into here, you have -4 divided by 1. Turns out it's negative. Region 2 is a negative region. And so we have a negative slope. It's a decreasing region. Now, if this was a critical point, you might think, oh, this is going to be a maximum. But this is not a critical point. This is a vertical asymptote. So what this says is, on the left-hand side of this asymptote, the function is going to be increasing. But on the right-hand side, it's decreasing. So to answer my questions, increasing for x negative infinity to 0. So I go from here to my vertical asymptote. and it's decreasing for x 0 to positive infinity. And there are no maxes or mins. Now, actually, I have a graph of this function, and we'll see if we look at the actual graph whether it makes sense. So here's what it actually looks like. So you can see here, it's like we have a vertical asymptote at x equals 0. And you can see here that as we go up, these lines are getting closer and closer to the asymptote, but they're never going to touch it. And you can see here it's an increasing function, and it keeps increasing. And then as soon as we jump over the asymptote, all of a sudden my function is decreasing. And you can see there are no maxes or mins. There's no place on this graph where the graph is horizontal or level. So there's no maxes or mins, but the first derivative does change. It goes from positive to negative. So just as I was explaining at the beginning of class, critical points, we know oftentimes that's where the first derivative can change signs on either side of a critical point. But now we have a case where the first derivative actually can change signs on either side of a vertical asymptote. Now, for a vertical asymptote, it may not change signs. Like for instance, this example I just made up here, this is a decreasing function. The first derivative is negative. When I jump over the asymptote, when I go here, this is still a decreasing function. So here's a case where on either side of the vertical asymptote, the first derivative is negative. So sometimes, maybe most of the time, when we look at some examples, the sign of the first derivative may not change on either side of a vertical asymptote, but there are cases where it does change. So that's why when we look at these rational functions, we have to analyze both critical points and vertical asymptotes. For this first example, all we had was a vertical asymptote, no critical points. However, let's do this next example, because I think for this example, we will have both critical points and vertical asymptotes. So this next problem is x squared over x minus 2. So let's go ahead, let's determine if we have any vertical asymptotes. That's pretty straightforward. Once again, all I'm looking at is the denominator. What value of x would cause the denominator to be 0? Well, pretty obvious, right? If x equals 2, then I've got a 0 in the denominator. So I do have a vertical asymptote. Now for the critical points, I have to take the first derivative. So here I'm going to use a quotient rule, right? So low d high, derivative of x squared is 2x, minus high d low, derivative of what's at the bottom is just 1, over the denominator squared. So if I try and simplify this, if I multiply this parenthesis, it's 2x squared minus 4x minus x squared over x minus 2 squared. So 2x squared minus x squared is just x squared. So it looks like it's going to be x squared minus 4x over x minus 2 squared. So there's my first derivative, sort of simplified. To find the critical points, I'm going to take that and set equal to 0. So now here's a little shortcut, right? when you have a fraction equal to 0, the solution is you can just take the numerator and set it equal to 0. So let's do that. And actually, let's factor out an x. So it looks like I have two solutions, 0 and 4. So those are my critical points. So I have a vertical asymptote and two critical points. So now I go, and when I do my little chart or my graph, I have to include both vertical asymptotes and the critical points. So it looks like a critical point is 0 and 4. And then the vertical asymptote was 2. And once again, so here you see why I put the little square around my vertical asymptote. So I know that these are critical points and this is a vertical asymptote. And oftentimes I need to keep that in mind as I work out these problems. So that means I'm going to have now 4 regions. So once again, just to say this one more time, critical points and vertical asymptotes are places where the first derivative can change signs. So we have to look on either side of the critical points and on either side of the vertical asymptote. So I'm going to have 4 regions. I need to choose a test point in each region. I'll choose -1 in region 1. How about I'll just choose 1 in region 2. Region 3, I'll choose 3, and I'll choose 5 in region 4. So once again, here is let's write my first derivative in sort of factored form. X times x minus 4 over x minus 2 squared. So for each region, I'm going to plug in the test point, and all I really care about is whether that first derivative is a positive or negative number. And what's interesting is if you look at this denominator, since I'm squaring the parentheses, the denominator is always going to be a positive number. So the denominator is always positive. So really, what's going to determine the sign is what's going on up here in the numerator. So for region 1, when I plug in my test point -1 into my derivative, what's going on in the top? You have -1, -1. So this parentheses negative. X out here is negative. 2 negatives make a positive. Turns out region 1's positive. So we can imagine that our function is increasing. Region 2, now I'm looking at a test point of 1. When I stick 1 in here, 1 minus 3 is -3, so the parentheses negative, but now this x is positive, so positive times a negative is negative. Region 2 is actually a negative region. Since this is a critical point, it looks like I'm going to have a maximum when x equals 0. So in region 3, my test point is 3. So I plug in 3 into here. 3 minus 4 is still negative, and 3 is positive. So region 3 is a negative region. So what's interesting, for this asymptote, it's negative on both sides. So the function is going to be decreasing, and then we jump over the asymptote, the function is still going to be decreasing. And then finally for region 4, let's see what happens when x is 5. So I plug in 5 in my first derivative. So now the parenthesis 5 minus 4 is 1, so it's positive, and a positive here. So now region 4 is a positive region. And since x equals 4 is a critical point, looks like I have a minimum. So I have a maximum at x equals 0, a minimum at x equals 4. And I do have a vertical asymptote. So to answer my questions, where do I have increasing regions? Well, it looks like region 1 and region 4. So it's increasing from negative infinity to negative 1 and from 4 to infinity. Where is it decreasing? Looks like regions 2 and 3. So from 0 to 2 and 2 to 4. So I have to break these up because I've got this asymptote here. So it looks like I have a maximum when x equals 0 and a minimum when x equals 4. And once again, I went ahead and did the graph of this. So let me show it to you and then I'll read off what we found. So we found, so in terms of the region, let's look. So the vertical asymptote is right here at 2. So you can sort of see that. That's where there's a break in the graph. We found a maximum at x equals 0 right here and a minimum at x equals 4. These are pretty gradual. It's hard to see, but you can see that it goes up and then it goes down, and over here it's down, then goes up. So there are maxes and mins. And we said it's increasing from negative infinity to, oh, sorry, I wrote this incorrectly. Sorry. This increasing is negative infinity to 0. Sorry about that. So increasing negative infinity to 0 and from 4 to infinity, and decreasing from 0 to 2 and from 2 to 4. So here's an example of, here are my 2 critical points, and this was the vertical asymptote. All right, one more example, just because these can be a little tricky. Last one. I'll try and go through this pretty quickly now since I've explained everything, hopefully. So now we have x squared over x squared plus x minus 6. And I'm going to go ahead, if I'm going to try and find the vertical asymptotes, I need to be able to factor this denominator. And it turns out it factors into x plus 3 times x minus 2. So it looks like in this case, I'm going to have 2 vertical asymptotes. X equals negative 3 and x equals 2. Now to find the critical points, I've got to go take first derivative, set it equal to 0 and solve that. So I'm going to have to use the quotient rule again. So with these rational functions, you almost always have to use the quotient rule, since you got like a fraction here. So low d high, derivative of the top is 2x, minus high d low, derivative of the denominator is 2x plus 1 over the denominator squared. So this is getting pretty messy. So what I need to do is I need to simplify the numerator, multiply out parentheses. So this 2x distributed here, you get 2x cubed plus 2x squared minus 12x. And then I need minus x squared distributed in here, so minus 2x cubed minus x squared. And let me just write this, because right now I'm really trying to simplify this numerator. So 2x cubed minus 2x cubed, that's nice. Those cancel out. 2x squared minus x squared is just going to be x squared, then minus 12x, or x squared plus x minus 6 squared. So to find the critical points, now here's our first derivative, maybe just for fun, because later on we're going to have to analyze this. So maybe factor out an x. So now to find the critical points, set that equal to 0. So now once again, we have a fraction equal to 0. If you're going to solve it, basically just take the numerator, set equal to 0. And actually, hopefully we can just see right now that the critical points are going to be 0 and 12. Now I'm going to check because I'm a little worried that I may have I'll make sure I didn't make any math errors here. So let me make sure I did my multiplication. It's always good to check because I did this problem before. I want to check and make sure. I'm going to look at my notes because I don't want to make a mistake in this video. So hang on one second. I want to look at my notes from earlier. I don't want to mess up. Yeah, it seems like oh, you know what I did wrong? I wrote down the initial problem wrong. So, well, let's go ahead and let's finish this. This is a different problem that I thought I was doing, but I think it's still okay. So, sorry about that. Let's go ahead, and the critical points are going to be x equals 0 and x equals 12. And here are my asymptotes. So now I've got to mark all these points. So I've got a asymptote at -3. I've got a critical point at 0, a asymptote at 2, and then a critical point at 12. Wow. So I've got 1, 2, 3, 4, 5 regions. So if test points -4, about -1, about 1, about 3, and 13. So I've got to go now and look at the first derivative in each region. So I'm going to try to do this quickly. So here's my first derivative. X times x minus 12. And actually, you know what? Since its bottom is squared, the bottom's always going to be positive. So once again, the whole key is what's going on in the numerator. So I can do this pretty quickly. Because I plug in -4 into here, it's a negative times a negative. Region 1 is a positive region. Region 2, and I plug in -1, it's still negative times a negative. So region 2 is going to be positive. Region 3, when I plug in 1, I get a negative times a positive. Region 3, it's actually going to be a negative region. Region 4, I'm looking at plugging in 3, I get a negative times a positive. Once again, region 4 is negative. And then finally, region 5, when I plug in 13, positive times a positive. So you can see here my critical points, just like at 0, I've got a maximum. And at 12, I have a minimum. And then here are my asymptotes. So to answer the questions about increasing, decreasing, and maxes and mins, increasing is region 1, 2, and 5. So negative infinity to negative 3, negative 3 to 0, and 12 to positive infinity. Decreasing, regions 3 and 4, 0 to 2 and 2 to 12. And then I have a max at x equals 0 and a minimum at x equals 12. Now I have printed out this graph, but I didn't make it the scale enough to see this minimum. But you can see, first of all, it looks like this. And there were 2 asymptotes at -3 and 2, which we have here. We said there's a maximum at 0 right here. It's pretty subtle, but you can see it goes up and comes down. And you can see increasing, right? Increasing, and then decreasing on either side of this asymptote. And then way out here, where you can't really see it, very gradually, this thing starts to go up again, this graph at 12. So the key thing I want you to see is that when you have these rational expressions, when you break up your graph into regions, you have to include both vertical asymptotes and critical points to see what's going on.